Now for lecture 5, I want you to read 3.3 again. I'm not going to though, it's recorded, it's in the last video if you want to go over it again that way, but it's 3.3 again and then 3.2. So I'm just reading 3.2 for lecture 5. Approximate solutions and bisection search. Imagine that someone asks you to write a program that prints the square root of any non-negative number. What should you do? Look them in the eyes and ask them why. Why would you want me to write that? You should probably start by saying that you need a better problem statement. For example, what should the program do if asked to find the square root of 2? The square root of 2 is not a rational number. This means that there is no way to precisely represent its value as a finite string of digits, or as a float. So the problem, as initially stated, cannot be solved. The thing a program can do is find an approximation to the square root, that is, an answer that is close enough to the actual square root to be useful. We will return to this issue in considerable detail later in the book, but for now, let's think of close enough as an answer that lies within some constant, call it epsilon, of the actual answer. The code in figure 3-4 implements an algorithm that prints an approximation to the square root of x. First, we create a variable called epsilon that we set to the value 0.01. Then a variable step, which we set equal to epsilon to the second power. Variable num guesses, starting out at 0, and the variable ans, starting out at the float 0.0. Then while the absolute value of ants squared minus x is greater than or equal to epsilon and the value of ants is less than or equal to the value of x, then ants plus equal step update the value of the variable ants to with the value of step by 1 step plus equal it, right? And update the value of num guesses by 1. This is just the same, the plus equal, I don't know if they covered this yet. The plus equal is just the same as if you said num guesses equal num guesses plus 1. There's just a more concise way of saying add 1 to it. Then print number of guesses equals, then the current value of num guesses, and if the absolute value of ants squared minus x is greater than or equal to epsilon, then print failed on square root of the value of x. Or else, print the value of ants followed by is close to square root of the value of the variable x. This is approximating the square root using exhaustive enumeration. Once again, we are using exhaustive enumeration. Notice that this method for finding the square root has nothing in common with the way of finding square roots using a pencil that you might have learned in middle school. I used a pen. It is often the case that the best way to solve a problem with a computer is quite different from how one would approach the problem by hand. If x is 25, the code will print number of guesses equal to 49,990, followed by, on a new line, 4.9990000000000 something or other 1688 is close to the square root of 25. Should we be disappointed that the program didn't figure out that 25 is a perfect square and print 5? No. The program did what it was intended to do. Though it would have been okay to print 5, doing so is no better than printing any value close enough to 5. What do you think will happen if we set x equal to 0.25? Will it find a root close to 0.5? No? Alas. It will report number of guesses equals 2,501, failed on square root of 0.25. Exhaustive enumeration is a search technique that works only if the set of values being searched includes the answer. In this case, we are enumerating the values between 0 and the value of x. When x is between 0 and 1, the square root of x does not lie in this interval. One way to fix this is to change the second operand of and in the first line of the while loop to get while the absolute value of and squared minus x is greater than or equal to epsilon, and ants times ants is less than or equal to x. When we run our code after this change, it reports that 0.4898999999999999962237 is close to the square root of 0.25. Now, let's think about how long the program will take to run. The number of iterations depends upon how close the answer is to our starting point, 0, and on the size of the steps. Roughly speaking, this program will execute the while loop at most x over step times. Let's try the code on something bigger, e.g. x set equal to 123,456. It will run for quite a while, and then print number of guesses equals 3,513,631, failed on square root of 123,456. What do you think happened? Surely, there is a floating point number that approximates the square root of 123,456 to within 0.01. Why didn't our program find it? The problem is that our step size was too large, and the program skipped over all the suitable answers. Once again, we are exhaustively searching a space that doesn't contain a solution. Try making step equal to epsilon cubed and running the program. It will eventually find a suitable answer, but you might not have the patience to wait for it to do so. Roughly how many guesses will it have to make? The step size will be 0.000001, and the square root of 123,456 is around 351.36. This means that the program will have to make in the neighborhood of 351 million guesses to find a satisfactory answer. We could try to speed it up by starting closer to the answer, but that presumes that we know the neighborhood of the answer. The time has come to look for a different way to attack the problem. We need to choose a better algorithm rather than fine-tune the current one. But before doing so, let's look at a problem that, at first blush, appears to be completely different from root finding. Consider the problem of discovering whether a word starting with a given sequence of letters appears in a hard copy dictionary of the English language. Exhaustive enumeration would, in principle, work. You could begin at the first word and examine each word until either you found a word starting with a sequence of letters, or you ran out of words to examine. If the dictionary contained n words, it would, on average, take n over 2 probes to find the word. If the word were not in the dictionary, it would take n probes. Of course, those who have had the pleasure of looking a word up in a physical rather than online dictionary would never proceed in this way. Fortunately, the folks who publish hard copy dictionaries go to the trouble of putting the words in lexicographical order. This allows us to open the book to a page where we think the word might lie, e.g. near the middle for words starting with the letter M. If the sequence of letters lexicographically precedes the first word on the page, we know to go backwards. If the sequence of letters follows the last word on the page, we know to go forwards. Otherwise, we check whether the sequence of letters matches a word on the page. Now, let's take the same idea and apply it to the problem of finding the square root of x. Suppose we know that a good approximation to the square root of x lies somewhere between 0 and max. We can exploit the fact that numbers are totally ordered. That is, for any pair of distinct numbers, n1 and n2, either n1 is less than n2 or the reverse, n1 is greater than n2. So we can think of the square root of x as lying somewhere on the line between 0 and max, and start searching that interval. This is like the whole dictionary from A to Z. Since we don't necessarily know where to start searching, let's start in the middle. Open the book up in the middle around M, our first guess. If that is not the right answer, and it won't be most of the time, okay, life's tough, ask whether it is too big or too small. If it is too big, we know that the answer must lie to the left. We can discard this whole region. If it is too small, we know that the answer must lie to the right. We then repeat the process on the smaller interval. Figure 3-5 contains an implementation and test of this algorithm. First, create and assign a variable epsilon to equal 1/100th. Then create a variable num guesses and low, and assign simultaneously values of 0 to both of these variables. Then create a variable high that we set equal to 1 and x passed in as arguments to the max function. Set the variable ands equal to high plus low divided by 2. And then while the absolute value of ants squared minus x is greater than or equal to epsilon, print low equals, then the variable low, high equals, then the variable high, and ants equals, the variable ants. Add 1 to our variable num guesses, update it, adding 1 to it. If ants squared is less than x, then update the value of the variable low equal to the current value of ants. Or else, update the value of the variable high to the current value of the variable ants. Then, update the value of ants equal to high plus low over 2. Finally, print the number of guesses followed by the number of guesses. Print variable ants followed by is close to square root of followed by x. This is using bisection search to approximate square root. When run for x equals 25, it prints all of this shit. I'm not going to read all that. You can pause. I mean, it's just to illustrate the idea. Notice that it finds a different answer than our earlier algorithm. It takes 13 guesses and arrives at something very, very, very close to 5, saying that's close to square root of 25. That is perfectly fine since it still meets the problem's specification. More importantly, notice that at each iteration of the loop, the size of the space to be searched is cut in half. For this reason, the algorithm is called bisection search, which literally means to cut into two. Bisection search is a huge improvement over our earlier algorithm, which reduced the search space by only a small amount each iteration. Let's try x equaling 123,456 again. This time, the program takes only 30 guesses to find an acceptable answer. How about if x equals 123,456,789? Takes only 45 guesses. There is nothing special about using this algorithm to find square roots. For example, by changing a couple of 2's to 3's, we can use it to approximate a cube root of a non-negative number. In Chapter 4, we introduce a language mechanism that allows us to generalize this code to find any root. Bisection search is a widely useful technique for many things other than finding roots. For example, the code in Figure 3-6 uses bisection search to find an approximation to the log base 2 of x, i.e. a number, ants, such that 2 to the nth power is close to x. It is structured exactly like the code used to find an approximation to a square root. It first finds an interval containing a suitable answer, and then uses bisection search to efficiently explore that interval. Actually, if you just want to pause and look at that, because it is just a re-implementation of the same thing, I'm not going to read it out. Bisection search is an example of a successive approximation method. Such methods work by making a sequence of guesses with the property that each guess is closer to a correct answer than the previous guess. We will look at an important successive approximation algorithm, Newton's method, later in this chapter. Finger exercise. What would the code in Figure 3-5 do if x was set equal to negative 25? Finger exercise. What would have to be changed to make the code in Figure 3-5 work for finding an approximation to the cube root of both negative and positive numbers? Hint: think about changing low to ensure that the answer lies within the region being searched. Finger exercise. The Empire State Building is 102 stories high. A man wanted to know the highest floor from which he could drop an egg without the egg breaking. Dumbass. He proposed to drop an egg from the top floor. If it broke, he would go down a floor and try it again. He would do this until the egg did not break. At worst, this method requires 102 eggs. It will. Implement a method that at worst uses 7 eggs. Done.